Okay. First of all, an anonymous student gave me an anonymous gripe this morning that the exam was no fair because the pulley problems weren't covered adequately. I won't say who made that gripe. For the record, the exam had 3 pulley questions. 2 of the 3 were in lecture. Okay, for the record, in lecture, you can see it in the notes, you can see it in the video. Are there any other complaints? Okay, tell your friends who weren't in lecture who you hear griping about the pulley problems, that they were there. Okay, any other questions or comments of any kind? Yes? Prelim 2 has the same regrade policy as Prelim 1, and Prelim 3 will have the same policy again. And the due date for that, you have the exams, you have the solutions. It seems like Tuesday with your homework is adequate. Is that true? Any complaints about that? Regrades and what? Corrections. You mean you don't like the way it was graded? Okay, let's start from the beginning. If you have a problem with the way your exam was graded, that's a totally separate issue, dealt in private, anytime, any place. Okay? If you want to raise your grade and you got below a 20, you can do that by redoing it perfectly, hopefully not by copying the solutions, perhaps incorrect solutions on the website. Not intentionally incorrect, but everybody makes mistakes. You have to do that by next Tuesday. Is that clear? Yes. Hand them into the box. Any problems with that? I don't really care. I'm just making up a date. Just seems like a good one. Yes? You don't need to have a reason for it. Does anybody prefer Thursday to Tuesday? Okay, Thursday. Any other questions or comments? Okay, so today I wanted to talk about rolling, and if we have time, go on to collisions. Last time I started an example in last class, which is something rolling down a ramp. If you want a cartoon of this, you can have a thing like this, and if a thing like this is on a tilted surface, it will roll down that surface, and we can calculate the acceleration and the ground reaction force and so on. It's not a hard problem, but you have to learn how to do it carefully, systematically, and so on. Now that thing which is rolling could be a uniform disk, and that this object I have here is a very good approximation of a uniform disk. It has a little bit of a hole in it, but that's just a little hole. It's a very uniform disk. But it could also be something like a hoop, which would be like my wedding band if it could roll without falling over. Or a pipe, if I rolled it down, would be like a hoop. And these things are different from each other in that they have different moments of inertia about the center of mass. And then a simpler problem, which you should know inside and out now, is like a block which slides without friction. So let's just start out and imagine we had a race between these, and we'd like to know what the ranking is from fastest to slowest of these things. So we're going to neglect air friction, and we're going to neglect what's called rolling friction, which is a torque which exists at this contact point if we make it not a point but a distributed contact that takes into account the deformation. If you didn't know what I just said the past 30 seconds, forget it. It's a topic we're not going to cover here, rolling resistance. So it's rolling. There's friction which keeps systems sliding. That there's friction doesn't mean it is sliding. There's friction that prevents it from sliding. How big is that friction force? We don't know. It is better turn out to be less than mu n, or else we've made a false assumption about that it's rolling without sliding. And we'll assume this is rolling without sliding. There's a little cushion of air here that has no viscosity. And we'd like to rank these from fastest to slowest, like we want to imagine that we're going to have a race between these things. And it could be, say, that the block goes the fastest, and then the disk, and then the hoop. Or it could be that maybe the hoop goes the fastest, and then the disk, and then the block. Or it could be that the block goes the fastest, and then the hoop, and then the disk. Or it could be that the disk goes the fastest, and then the hoop, and then the block. Or it could be either none of the above, or cannot be determined. Cannot be determined would be, for example, if you need to know what the radius is of the disk, or you need to know what the slope is, or you need to know what the gravity constant is. There's other information needed besides just which of these things it is. Okay, so let's say we're going to pick between these, and imagine that you're on the spot, and you're going to be graded on your choice, and you got to vote. And then you wake up and your fantasy is true, and you actually do have to vote, and your grade does depend on it. You're going to get 1 extra point, 5 instead of 4 on 1 clicker question. The probability that this could change your grade from, say, a B to a B plus or something like that is about 1 in 10,000. So go for it. Vote. Any questions about the question? Okay, 5 seconds left. 5, 4, 3, 2, 1. The votes are in. Are you sick back there? Are you sick? Come sit forward. Okay. What do we have? Hoop, disk, block seems to win. In second place, we have D, disk, hoop, block. And in third place, we have A, block, disk, hoop. Fourth place, C. Okay, so how do you work out a problem like this? Well, we can always go through the details. We can do the calculation. If you don't know how to do the calculation, which probably you should be able to do, but I'm going to show you anyway, we'll do the calculation. We'll get an answer. We'll be able to calculate the acceleration. Whichever has the biggest acceleration wins the race. Because if they start from a stop and one has a bigger acceleration, then when you integrate, it has a bigger velocity. And when you integrate again, it has a bigger position at each time. The one with the bigger acceleration wins the race. Calculation will show that. What if we want to get some intuition and just sort of get an answer, say, to something like this? I think the easiest way to get this intuition is actually by an energy calculation. So this system has 1 degree of freedom. Either the hoop or the disk or the block have 1 degree of freedom. That means 1 number is needed to describe the position. Now, in the case of the rolling and the sliding, there are 2 numbers floating around. One is how far it's gone, and the other is how far it's rotated. But they are coupled. If you know one, you know the other. So the system only has 1 degree of freedom. Now, had we been doing this disk and it was sliding, and we didn't know what the coupling was, then we could say it has 2 degrees of freedom, rotation. But this problem, as stated, has 1 degree of freedom. All 3 problems, 1 degree of freedom. There is no source of energy dissipation in this problem. Where does energy dissipation come from? It comes from friction, air friction, sliding friction. There is a friction force down here at the bottom of this disk. We go in close up, zoom in, and look at the disk. Look at the force down here. There's a normal force and also a tangential force. But the work of this force is the force times the velocity of the point that is touching. And this contact point has 0 velocity. We spent a lot of time on that last class. Therefore, there's no work done by this force or done on this force. So this force has no effect on the energy of this system as it rolls. And that's also true for the block, which is sliding, because the velocity is not zero, the relative velocity, but is perpendicular to the force for the sliding block. So in all cases, this is what's called a conservative system. There's no dissipation. So we have energy conservation. So for all of these problems, the work done by gravity when this rolls down is equal to the change in kinetic energy. For the block, the kinetic energy is just 1/2 mv squared. For the hoop and the disk, the kinetic energy is the energy of translation plus the energy of rotation. So for a given velocity, the hoop and disk have bigger energies. Let's just say all the masses are the same. And for a given angular velocity, the hoop has a bigger kinetic energy than the disk does. So if they all have the same velocity, then the block has the smallest kinetic energy, the disk the medium, the hoop the biggest. But that's not the way this problem goes. When you go from the top of the hill to the bottom of the hill, they all have the same work done on them. Let's say they all have the same masses. Therefore, they all have the same kinetic energy. The block gets to spend all of that kinetic energy on 1/2 mv squared. The disk and hoop have to spend that kinetic energy partially in translational and rotational energy. And the hoop has to spend more of it on rotational energy because there's a bigger moment of inertia. So in order for them to have the same energy, the block gets to go the fastest, the disk the mediumest, and the hoop the slowest. So the right answer here is E. What did the professor say? A? Okay. We lock that up. Okay, so if we do the energy analysis, we have that the work is equal to the change in the kinetic energy. The work is mgh when we go from the top to the bottom. And the change in the kinetic energy is just the final kinetic energy, because the initial kinetic energy is 0. The final kinetic energy is 1/2 mv squared plus 1/2 I omega squared. But omega, whether we pick it as positive v over r or negative v over r, doesn't matter because we're going to square it. So omega squared is equal to v squared over r squared. So this all turns into 1/2 m plus I over r squared times v squared. Let me get this right. I'll not do the algebra in my head. I'll just do the terms separately. It turns into 1/2 mv squared plus 1/2 I over r squared v squared. And therefore, I equals 0, which is the block, is the fastest. And I equals 1/2 mr squared, which is the disk, is next. And I equals mr squared, which is the hoop, is the slowest. So it's a quick calculation. Now we could also use energy balance to get the differential equation. So for a 1 degree of freedom system, we can use energy to get equations of motion. And what do we mean by equations of motion? We mean we can calculate the accelerations from the positions and the velocities and the parameters. How does that work? Well, it says the power of the forces is equal to the rate of change of the kinetic energy. That comes from the derivative of the previous expression. So that comes from mgh dot with a minus sign. If we say h increasing is going up, the power is the rate at which h is going down. It's the rate of change of potential energy. Is equal to ek dot. That's 1/2 mv squared. I'll just put it here as d by dt of the expression 1/2 mv squared plus I over r squared v squared. What's h dot? Well, if we go down here, d, the rate of change of h is d sine theta, so it's d dot sine theta. So this is minus mg d dot sine theta. D by dt of this expression over here is 2 and 2 cancels, so we have m v v dot. That's d by dt of this expression, plus I, there's a 2 here, over 2, and that 2 cancels that thing, I over r squared v dot. But v and d dot are the same thing. D dot equals v. We can cancel v from both sides, assume it's not 0 all the time, and we get minus mg h dot. H dot minus h dot is d dot sine theta, so this is a plus sign here. So we get mg sine theta is equal to m plus I over r squared v dot, or v dot is equal to, now m's cancel out, kind of, if we put I over mr squared down here. So we get a g sine theta over 1 plus I over mr squared. So we get that answer just from energy balance. Look at it, ask me questions, or ask me to talk through any part. Yes? H dot was how much h is going up. Minus h dot is how much is going down. D, I already picked, is going down the slope. So d dot sine theta is how much is going down. That was the minus h dot. Yes? How did I cancel the mass? Is I've stuck it down here. When I canceled that, I had to stick the m down here. Any other questions? Okay, one thing you notice is that the answer here depends on g, but the relative speeds, remember we had this relative speeds issue right up there, only depends on this quantity here. So the difference between these three problems, the block, the hoop, and the disk, is this quantity. And this here only is 0 for the block. And for the disk and the hoop, this ratio is independent of the radius or of the mass. Going back to this reasoning over here, to do this reasoning, I said, oh, we have the same work both ways, but maybe the answer depends on the mass. Like I assumed that they all three had the same masses. To make this reasoning careful over here, it had to be that two blocks with different masses go down the hill with the same speed, same acceleration. Or two hoops with the same masses, or two hoops with different different masses, two hoops with different radiuses. So how do we work that out? For example, that the acceleration here does not depend on the mass. We can go through the algebra, and the mass will cancel out. But intuitively, how can you know this? Well, what if I put one block on this slope? What will the accelerations be? It's whatever it is, right? G sine theta. If I took two blocks next to each other, each of them will have the same acceleration. And if I connect them with a thread, it doesn't change anything. And if I glue them together, it doesn't change anything. So now all of a sudden I've got a mass with twice the mass that has the same acceleration. So that's how you can see the mass does not affect the answer. And the same is with the disk. I put a disk here. I put a disk next to it. They both will have the same acceleration. I glue them together. It doesn't change anything. It has the same acceleration. So the answer for the disk or the hoop or the mass doesn't depend on the mass. Now maybe for the disk or the hoop, the answer might depend on the radius, and that scaling is a little more subtle. And if you have trouble with that, I think the only way to get that is to do the calculation. If you want to do it intuitively, the kinetic energy, for example, only depends on the translation speed, the translational part of it. The rotational part of it depends on the motion relative to the center of mass. And for example, if this point has a speed of v, this one has 2v independent of the radius. So the partitioning of the energy into the translational and rotational parts is radius independent for this problem. Okay, now let's work this out with F equals ma. Which is the reliable fundamental way of doing things is with linear or angular momentum balance. Yes? Say again? For this one or for the hoop? Yes? There's not really mass in this formula because the I is either mr squared or 1/2 mr squared. So the mass is not really in this formula. Yes? Other questions? Are you happy with that? Okay. Okay, the reliable thing, the fundamental thing is linear and angular momentum balance. By law, you're not allowed to use linear angular momentum balance unless you draw a free body diagram. So we've got to draw a free body diagram. We put things which are in the system, we draw clearly. Things which are not in the system, we draw with dotted lines. We have a normal force and we have a friction force. We can label this point as C. We can call this N. We can call this the friction force, and we also have mg here. In case anybody wants to know about it, or we're going to use it, we can make a convenient coordinate system, I, j, lambda, n. We can mark a distance that this thing travels. We want to not make it look like an arrow on the free body diagram, so we've used a dotted line. So it's very clear which are the forces on the free body diagram. How do we figure out that forces? We cut this free from the Earth and put an mg. We cut it free from the ground and looked at the force of the ground on the object. There's a force normal to the ground that prevents penetration, and there's a force tangent to the ground which prevents the slipping. How big is this force? It's not mu n. It's something less than or equal to mu n. Which direction is it? I don't know. Oh, actually, I do know because I've done this problem 1,000 times. But to draw this free body diagram, you don't have to know. Yes? Did I say there was no friction? I do not believe I ever said there was no friction. I said it was rolling, and in order to enforce it to roll, there has to be friction. But it's not mu n. If there's a friction coefficient of mu, we have to just calculate the force and make sure it comes out less than mu n. That is, that the friction coefficient was big enough to prevent sliding. If I take this table and I tip it enough, when I roll this thing down, it will slide. And is there some harmless way I can do this demonstration? If I try to slide this down here, it slides. That means the friction coefficient wasn't big enough. If I do it like this, it rolls. The friction coefficient is big enough. When it's rolling, how big is the friction force? We don't know. We have to calculate it as a constraint force. Does that address your question? Yes? You are quoting information from another course. I have never talked about static friction in this class. I did give a small lecture about it, which is that I wrote my PhD thesis about static friction, and it's a morass of complicated stuff which is easiest to just avoid. So in this class, the static coefficient is equal to the dynamic coefficient. And I recommend that you use that for the rest of your life also, unless you know enough to know better. Yes?
Is mu a constant based on the material properties of the object in contact, or does it matter, is it based on the angle?
Mu is said to be a material property. It's not a very reliable one. So there's some not reliable material properties we use in this class. The two main not reliable properties are mu and E, the coefficient of restitution. E is even worse because it depends not just on the surfaces but the shape of the objects. Mu depends on the material properties, supposedly, but I think I told you Jaeger's law of friction. First is that the friction coefficient is usually between about 0.1 and 1. Not always. It can be smaller or bigger. Second is the friction doesn't depend on the normal force. The coefficient doesn't, or that is the friction force is proportional to normal force. And the third law of friction, Jaeger's third law of friction, is a friction experiment will make a monkey out of you. That is, if you try to measure the friction coefficient between two objects, you will find it varies from day to day, hour to hour, whether you breathed on it or not, whether you touched it or not, or so on. It's not a reliable number. So it's said to be a material constant, but it's not a very robust one. Unlike, for example, Young's modulus from TAM 2020, which is very reliable. Does that address your question? Are you happy with the, Michelle, are you happy with the static coefficient of friction? Let's see. I think I gave a whole lecture about this. You could watch the video. But the short story is if you plot the friction force divided by the normal force as a function of the sliding velocity, where if you take two things, one's like this and one is sliding like this, and here's this normal force, and when you cut this free and you draw the free body diagram, there's the normal force and there's the friction force resisting this velocity. In this picture, the friction law that I recommend you use is represented by this curve. It says when they're sliding, the friction force is mu n. If it's sliding the other way, it's mu n the other way, or minus mu n. And if it's not sliding, you don't know what it is. It's somewhere on this line. If you look at other books, you will see that in disguise they are trying to say the same thing, which I just said. Does that address your question? Friction forces, or any forces, do work or have power if the velocity of the point they're touching is not zero. The power of a force is the force times the velocity of the point that's being touched. The bottom of something which is rolling has zero velocity. Therefore, the power of the friction force is zero. Does that address your question? Okay, other questions? Yes? It could vary with time. In this problem, it happens not to, but that was something you have to calculate. You don't know. If it's a roller coaster hill, it will vary with time. Okay, this disk has maybe some radius r, draw with the dotted line. It has, remember, some moment of inertia and some mass. We've got this point C, which is a nice point. Why is it a nice point? Because if we want to figure out the equations of motion, how this moves, and we don't care about these forces, we can use angular momentum balance about this point to figure that out. So if we take angular momentum balance relative to point C, what do we get? Is we get the sum of moments relative to point C. Same stuff you used in statics, but now it's not statics, it's dynamics, and that force is, in that moment, the forces and moments in general are balanced by the rate of change of linear and angular momentum. In particular, the torques about point C are balanced by the rate of change of angular momentum with respect to point C. What are these torques? On the left-hand side, we have the cross product of the position of G with respect to C crossed with minus mgi, J, which we can work out all the position vectors and sines and cosines, or you can do this one in your head. Before I go on, I'd like you to do this one in your head and then write down the next line. Write down the next line of the left side of that calculation without doing algebra. Okay, who's got it? Raise your hand. Who does not have it? Who didn't answer? Who neither has it nor doesn't have it nor didn't answer? All those people who didn't get the answer or didn't get the answer, didn't answer, please do not raise your hands. Good, perfect. Everything adds up. Okay, those of you who haven't got it yet, do you have any questions which would help you think about this? Let's try it another way. If you had to do it algebraically, does anybody have questions about how to do this left side of this equation just by writing vectors down and doing cross products and so on? Any questions about that? Does anybody want me to do that calculation? Okay, so everybody can do that. Is that correct? Raise your hand if you could do it given the time with vectors. And you couldn't? Then go back and take 20/20. Anyway, you should be able to do it. Now we want to do it without writing down all the sines and cosines and position vectors. How do we do it? We look at this thing, and we're just trying to figure out the torque of this force. Certainly that's proportional to the size of the force, so it's got to be proportional to mg. And what we're looking at is mg times the lever arm of this, how far this is sideways. And that's going to be, using the right-hand rule, it's going to be in the negative direction. Now certainly if this is bigger, then the torque is bigger, so it's proportional to the radius. And certainly if the slope is bigger, it's bigger also. But if the slope is 0 at 0, all of these things always are sines or cosines. It's 0 when the slope is 0, it's bigger when theta is bigger, it's got to go with sine theta. So we're just stuck with the answer being minus mg r sine theta k. But if you don't like what I just did, you can do out the algebra, but I recommend you get used to doing this kind of thing in your head so you can check things, think about things, do problems faster, and so on. Okay, on the right-hand side, what do we have? We have the position of g with respect to c crossed with mass times the acceleration of g. This is the term you get for rate of change of angular momentum of a particle. This is for particle dynamics, orbital mechanics, particle on a string, pendulum, and so on. If all you have is a particle, you have this term. So you're familiar with this from freshman physics, high school physics, and so on. Then there's another term which you had in freshman physics all the time also, which was this I alpha k. And this, unfortunately, in the freshman classes, you usually have this one in isolation. You don't have it together with this. So if all you have is something which is rotating but not translating, like a pendulum or a gear, the torque is equal to the rate of change of angular momentum associated with rotation. Because we live in a universe with a benevolent God, when we have both translation and rotation, we just add these two effects. It turns out it's not more complicated than that. Just we're that lucky. And you can work out the algebra to show that it's that lucky. It's in the book. It's in every book. But I don't want to, it's just a bunch of summations and integrals and grouping terms and so on. You can do that calculation, but we're lucky. There's this intuitive effect. When something's got big moment of inertia, it's hard to rotate. So the The bigger the inertia, the bigger a torque it takes to cause it to twist. And when something's got a bigger mass, it takes a bigger torque to cause it to go around things, proportional to the distance and the mass, and only the perpendicular part counts. And if you have both rotation of the object and translation, you add the two terms. Okay, this, as I've said, is our main formula for two-dimensional dynamics of rigid objects. Okay, now we want to work out what this term is. We can do this all with these funny cross products and so on. Here we have a d double dot lambda. That's the acceleration of the center of mass. It's just going in a straight line down the slope. Here we have an r times n. We can look at this and see this is perpendicular to this, or you can just look at the picture and see that the motion is perpendicular to the relative position. Therefore, this term is this radius times this d double dot times the mass. It's in the k direction, and it's minus, because if d double dot is positive, that term is pointing in the negative k direction. Or you can work out the cross products and get this answer. And over here, we get I alpha k. Now the problem with this expression is it has two unknowns in it. It has alpha in it, and it also has d double dot. What do we do about that? If we knew the friction force, we could take sum of moments about the center and calculate the alpha using the friction force. But we don't know the friction force because it's not sliding. And because it's not sliding, all we know about the friction force is that it's not so big as to cause sliding. So we don't know the friction force. We just know bounds on the friction force. Yeah? So you want to say this term is 0?
No. As in, when you're, if you're taking a moment about C and you make a or this kind of G, and what's the
If we take moments about G, which we can, then the rate of change of angular momentum is equal to the torque. The torque is this radius times force in the minus k direction. But we don't know what that force is. If it was sliding, if we were doing this problem where it's very steep and we know it's sliding, this problem where it's very steep and we know it's sliding, then we could put mu n there. We'd have to calculate n as a separate calculation, but we could do that from linear momentum balance. Okay, so we have alpha and d double dot. We only have one equation. It's a vector equation, but it's all in the k direction, so it's only one scalar equation. How do we solve for two unknowns from one equation? Yes? Right, so we have the kinematic constraint. That is, there's a restriction on the geometry. And this is just, in a way, like pulley problems, for example, or two masses connected by a string. This was the rolling constraint. And last class, we figured out, so you can look at the notes from last class or the video, we figured out that alpha, if we use the counterclockwise sign convention, is minus d r double dot. And that is completely wrong, as we can tell by checking the units. Here I'm now doing the problem of the accelerating radius disk. Rolling down a slope at 0 speed. Let's now change to the constant radius disk accelerating down the slope. Okay, so now we have equation star. We take equation star. It's only in the k direction, so pulling out the k component or dotting with k, we get on the left-hand side minus mgr sine theta. And on the right-hand side, we get this collection of terms, and we can decide whether we're more interested in D or more interested in alpha. I think I'm going to say I'm more interested in D. So I get minus R D double dot M sine theta. And then I get plus this other term, which is now a minus I D double dot over R. Say again. Some crazy part of my brain. It came from over here, but it escaped to the other side of the equation because I didn't contain it well enough. Okay, so now we get that D double dot is equal, and we can cancel the m's again, which sends an m down on this side of the equation, and we get G sine theta over 1 plus I over mr squared again. Now let's say somebody asked us, what is F? What is that friction force? Okay, spend 2 minutes, figure it out yourself. You're allowed to talk to each other. Do you have 2 questions? Quick, how are we going to figure it out? Somebody raise your hand and tell me. How? Sum of moments with respect to G is equal to I alpha K. What about the R cross MA term? Well, that was the position of G with respect to G, which is 0. Or, if you like, we're back to your freshman physics reasoning. We're just doing center of mass angular momentum balance. This thing, if we take the sign convention from this picture, this is a minus RFK. And this thing, we've already figured out. It's G sine theta over 1 plus G sine theta over 1 plus I over mr squared. Now that thing was D double dot, but actually what we needed for this thing was alpha. So to get alpha, we have to divide that thing by R and put a minus sign. So we have to put minus this thing divided by R, and this whole thing is alpha, and we're done. And that's K, and therefore we get F is equal to whatever it comes out equal to. How about N? Let's say we wanted to know N. How would we figure that out? Think about it for 10 seconds. Okay, someone tell me what the method is. Linear momentum balance. So we write linear momentum balance equation. What does that say? It says the sum of forces is equal to the mass times the acceleration. What do we know about these things? We have that n in the n direction plus f in the lambda direction, and I picked a sign convention that had a minus there. and we have minus mgj is equal to the mass times d double dot times lambda. If we take this equation, which is a vector equation, it has a mixture of i's and j's and lambdas in it. But if we take this equation and take the dot product of both sides with, I'm going to say that again, and then I'm going to make a pause, and you're all going to yell out the answer. I take that equation, and I take the dot product of it with, very good, n, then it gets rid of things which I don't know and don't care about, namely this and this. Actually, I do know them, but I could be interested in this answer before I did that calculation. And then all I'm left with is this term, and then I have an n dot lambda, and this just gives me what you would expect is mg cosine theta equals n. Okay, lastly, I want to do a demonstration. I'm not going to get to collisions, but I love this demonstration. I'm going to leave the calculation to you. I believe it's a homework problem. Yes? Could I find f? No, I could not, because if I use this linear momentum balance equation from the start without having done angular momentum balance, I'd have d double dot as an unknown and f as an unknown. It would be one equation in two unknowns. Or if I take this whole vector equation, all we can get is two independent scalar equations. We could dot it with a million different vectors, but we only get two independent equations, and we have three unknowns in here, d double dot and f and n. We could plug that in, and we did that. That's exactly how we did. Oh, that's a different way of doing this one. Yes, sorry. That's what you're saying is a different way to do that one. That would be fine, yes. Okay, I want to do this demonstration. It's on your homework. It's a beautiful example. If you're trying to really learn this course material, I think this problem is worth a couple hours of your time. Couple hours of your time. This is not a quick, easy problem. It's a hard problem. I want to take this and I want to pull the tablecloth out from underneath. When I do that, if you want, you can assume I do it slowly enough so this rolls. Or you could assume I do it fast enough so it slides the whole time. Or you could say you don't know, it rolls and slides. And the answer, the question has the same answer for all those three different conditions. When it gets to the end here, it's moving this direction and sliding. Eventually it stops sliding and it's rolling. And the question is, how fast is it rolling when it ends up rolling? And the answer is this wonderful thing. I think it's wonderful. This is testing your nerdiness by how wonderful you think this is. So I've got to find a sort of level angle on this table. Okay, ready? The answer is, there you go. So to get there without a long pages of calculation is a tricky little thing, interesting little thing. I think it's worth your time to think about it.